it will parallelly or silently open a TCP to do the FTP data transfer. Now, what is missing is about the commands. And after look at the transfer, you already have a sense that, right, FTP do everything in ASCII characters. The command is, that is a PAS, is password, and even not encrypted. Okay, so I will say this is ASCII message. It's also ASCII message. Okay, so then this is a table. You can skip it. I never put it in the examination. About if you want to type command manually. Okay, then I think it's the end of this chapter 2. Chapter 2 already we take three weeks to talk about it. Basically, we mentioned something. If you want to invent your own protocol, should it be persistent or not? Should it be stateful or not? Okay. In our assignment 1, tonight I don't have time. Tonight I have to go to another place. Okay. I will put an assignment 1 on Thursday. Okay. After the midnight. Okay. Then how about a header? What is the structure? You have to say something about this. Okay. So then it is time for me to have a beginning of chapter 3, part 1. Chapter 3, part 1. I have put the notes up, right? So let's take a look what this chapter is doing. Okay? Where's my laser? Okay. We were here. Okay? We look into applications. We look into ASCII protocol. We know protocols need to have a socket. Now we will dig deeper into the kernel. So in this chapter, what we can show to you will be something very abstract. I cannot really show the code to you. I cannot break into the kernel and say, stop, please don't say this thing. Okay? We have only done the analysis by doing a Wireshark capture. Capture the activity to see, oh, UDP, what you are doing, TCP, what you are doing. Okay? And we will first look into how it is implemented. Okay? What are the basic or common components? If it's a TCP, if it's UDP, they have some common things. Okay? So the common things I can skip it. Okay, it's just saying that. Okay, basically it's a process communication. If it's transfer protocol, and the transfer protocol is export to the OS level. Okay, because I don't think that you wish to know application, we need to start a affiliation now. Okay, basically this won't be a concern inside the application. So we start a function or a system call. Now, who has read my zip file on network, simple network? I guess no, right? I mentioned something. I mentioned socket system call. I mentioned port, buying system call for buying a port. I talk about read-write system call, listen, connect. Okay? So basically, which will cooperate with the kernel? Everyone will cooperate with the kernel, right? But which one will trigger network traffic? Is it the socket? I open the socket, then will trigger network traffic? Or the connect system call? Connect system call trigger network traffic? Or the read-write system call sometimes will trigger something wrong? Okay, we will look into it. And why there is some delay or some inaccurate phrase that I've just said. I've just said is read-write. Where it will fire a packet immediately, I will say that they will have delay. And the delay we can understand using some trace. Okay. And how about the disadvantage? The disadvantage, I already said it. Okay, it is a basically system call, blocking system call. Read is a blocking system call. Write is blocking system call. It involves IOs, so it is slow, and it will interrupt the operating system very, very frequently. So it is a, I would say, I/O bound process. Okay. So what is the thing in common for socket and to the transport layer? Now let's say this projector is good. Okay. The projector in ERP cannot distinguish these two colors. You will see a layer of gray. Okay. Now they can distinguish now very good. And what is this here is, say if I open a UDP or open a TCP, they will have their own transport layer data. And why I encode this guy? Look at this guy. What is this guy different from other guys? This guy is coming from the same process. So actually, I'm telling you one very important concept. I can have a process opening many sockets, and those sockets will connect to different hosts. Now, with this management of the socket under the same control, let's say that I have 10 connections. If one of the connection is very congested, I will also congest the remaining 9. Okay, which is not. We have a separated, of course not identical, separated data structure for each socket. Okay, it depends on what is the service you want. UDP, unreliable data transfer, then the data structure will be smaller. If it's unreliable, how can we read data, right? Our job is to fold it out. Okay, and say goodbye. And what is TCP? The data structure becomes bigger. TCP, at least I have to keep track. Oh, I have sent you for 1 minute. Why there's no reply? Okay, maybe we need a timer. Maybe we need to have buffer to buffer what I have just sent. And after 1 minute, no response. Then I fire another brother, sister, or the way sent to the networks. Okay, so why I say that they will have a different data structure is because of the purpose. Okay. And after processing it under the kernel, go through the structure, mark down all the things, it will go out of the transport layer control and go to the network layer control. Okay? Now I copy some keywords from the book. The book called this process multiplexing. I would say that encapsulation. So what is the difference? The difference is multiplexing is basically telling you that, a network is a big pipe, okay? But you are sending things from different processes. I basically touch all the things and push it into the big pipe, that's all. I won't agree with this, okay? This is a bad way to describe a network. To describe a network, basically you add something to represent this process, this socket, and this type of reliable and unreliable data transfer. After we add all the things, we want to send it out. We will package it just like we put something in a container. Put it in a box. And the box states that there is an IP address, and this is the place to add the IP address to choose which interface, which network interface it should go out. Let's say my previous computer was at Windows there, okay? I have a VMware interface. I have maybe a VPN interface. I want to send out something. Which interface is to choose? It is not the concern of TCP and UDP, but the concern of the network layer, the one who add the IP address, okay? And I just said that I will add something to the data so as to, let's say I send a data number 1, data number 2. At least I want to know a number, put a number there, okay? And usually that number has a name called sequence number, okay? I want which position of that packet is in the sequence. So we will have a header, okay, in blue, and this blue guys will indicate some special things about transport layer. Now, this is something about the application layer. We try this in chapter 2. Now, after I type it, I press enter. Immediately, kernel will put this extra data concatenated together. And at least we will have port number, source port, destination port, right? I never say anything about port in application. The port number I only mention is while we set up the connection, right? So I will say that, where I'm from, where I go to, and then package it together, we call it transport layer segment. And after it go out, it will go to another machine. It will go to another machine. And this is diagram that when I go to another machine, the network layer receive a packet and they look into it, it's just like something like this. When I look into it, it contains this guy and this guy. Okay, I'm a level layer. I look at it. Oh, two big things. Now I look at this two big things. Should I process the application? No, we seldom process the application. Okay, the network layer only look at these three guys. Okay, and by looking at these three guys, we determine. Now this is demultiplexing, or I would say de-encapsulation. I separate the data now. I look at the port number, source port, destination port, then I determine which process should I deliver that data to. Okay? So, add together, we become something big like this, adding together. We have a header, we have HTTP message. The header contains source port, destination port, because it's a HTTP server. The destination port is 80. I use a 13579 as a source port, set it out. What will happen? It will reach the other end, and the other end will already have two file descriptor, or I would say sockets, get prepared, because let's say previously I already have the connections established. So I will have these two guys. The moment is when these two guys arrive at this machine, these machines know that I should map to this file descriptor of this process and this file descriptor of this process, usually based on several things. First of all, the destination port. The machines know that port 80, you already buy port 80, I ship it to you. Okay, I ship to this process. But this process contains two file descriptors. Which file descriptor I should go? Then I will look at the source port. Whether the source port is 123, 13579. If the source port is that number should go to this. Else, go to this. And this is the way how we depend on the header in order to ship into the process. And inside the process, many connections, no problem. I know which connection I should go. Okay? So since time is up, I leave a tail there. The tail is what happened if I have something like this. Separate clients using the same port. I don't know why so happened. Separated. So that's why I can use the same source port. And when it arrives at there, which one I can go? If I base on the previous determination, the determination say that I only believe in the source port, then I have a trouble. I only know that I can ship to this process because of the destination port. But within that process, the kernel will get crazy. Hey, which file descriptor I should go? Or maybe I do a copy to give it all, right? Later, I will talk about it very easy. Okay? So let's stop here.